Your phone is sitting on the table, the screen is dark, no active data session, and yet a call comes in and it rings. How did the network find a sleeping device among millions? That wake-up process is called paging. In 5G, paging is the procedure the network uses to reach a user equipment, the UE, when that device is registered but idle. No dedicated radio connection, no continuous signaling, just a carefully aimed tap on the shoulder. Why it matters is simple. Idle phones save battery by listening only at scheduled moments. The core network must still deliver downlink data, SMS, or a voice invite. Paging is the bridge between power-saving silence and an active session. Get it wrong and you waste radio resources or miss the UE entirely. Get it right and the network feels instantaneous while devices sleep most of the time. In this lecture, we will walk the full 5G paging procedure. The states the UE must be in, who triggers the page, every field in the N2 paging message, the RRC request on the air, the UE's service request response, and 3 optional features that make paging smarter: policy differentiation, priority, and assistance information. Before any page can be sent, the UE has to be in a very specific pair of states. Think of registration and connection as 2 independent dials. Registration Management, RM, answers, does the network know this subscriber exists here? When the UE is RM registered, the Access and Mobility Management function, the AMF, holds a context for it. The UE has completed registration. The network can address it. Connection Management, CM, answers a different question. Is there an active non-access stratum signaling connection right now? In CM idle, that NAS connection is gone. The radio link is released. The UE is reachable only through paging in the tracking areas where it last registered. Put them together, RM registered and CM idle. The UE is known to the network but sleeping on the radio. That is exactly when paging is required. If the UE were CM connected, the AMF could already send NAS messages over the existing N2 connection. No page needed. If it were RM deregistered, there is no context to page at all. So the precondition is crisp: registered, idle, reachable on 3GPP access. Only then does the paging procedure start. Who actually starts a page? The short answer is the AMF, but the story is a little richer. The AMF itself can decide to page. More often, another network function nudges it. The Session Management function, the SMF, may have downlink data waiting in the user plane function for a PDU session. The SMS function may need to deliver a short message. Those NFs signal the AMF checks the UE's CM state, and if the UE is CM IDELE, the AMF requests paging from the radio access network. Here is the part that matters. The AMF is the mobility anchor for the control plane. It alone knows which tracking areas the UE is registered in and which GNB nodes serve those areas. So even when SMF or SMSF provide the reason, the AMF owns the page. A useful mental model: SMF says, I have a packet for this PDU session. AMF translates that into wake this UE in these tracking areas with this identity at this priority. The radio never talks to SMF directly for paging. Everything funnels through the AMF's N2 interface to the GNB. The happy path has 3 clean steps. Keep this map in your head. Every detail later hangs on it. Step 1. The AMF sends an N2 paging message to one or more GNB nodes. Those GNBs belong to the tracking areas where the UE is registered. The message is packed with identity, area list, DRX timing, priority, radio capability hints, assistance data, and paging origin. Step 2. Each GNB that receives the N2 page turns it into an air interface message, the RRC paging request. It pages the UE only in cells that sit inside the tracking areas listed for paging. The UE, in idle mode, wakes on its paging occasion and reads the paging channel. Step 3. When the UE sees its identity in that RRC page, for a PDU session tied to 3 GPP access. It does not just acknowledge, it initiates a UE-triggered service request with PDU session reactivation. That brings the NAS connection back, moves the UE towards CM connected, and lets the downlink data finally flow. 3 hops: core to radio, radio to device, device back into service. Next, we open the N2 message field by field. Open the N2 paging message. The source lists 7 critical pieces of information the AMF sends to the RAN. First, the NAS ID for paging, typically based on the 5G TMSI, the temporary mobile subscriber identity allocated in 5G. This is how the UE recognizes this page is for me, without exposing a permanent identity on the air. Second, the list of TAIs to be paged. Tracking area identities. The AMF does not flood the entire network. It scopes the page to the tracking areas where this UE is registered and considered reachable. Third, paging DRX, discontinuous reception. Idle UEs do not listen every millisecond. They wake on a cycle. The AMF tells the RAN which DRX cycle the UE is using so the GNB can schedule paging occasions the UE will actually hear. Fourth, paging priority, an optional indication that this page should be treated with higher urgency on the radio. Fifth, paging UE radio capability for paging, band support and related radio facts the RAN needs to page efficiently. Sixth, assistance data for paging, recommended cells and RAN nodes from earlier contexts. Seventh, paging origin, who or what motivated the page, useful for policy and diagnostics. Together, these fields turn a blunt "wake someone" into a precise, battery-aware, load-aware operation. Let us slow down on 3 fields students often blur together: identity, area, and timing. The NAS ID for paging is the UE's handle in the idle world. In practice, you will see 5G TMSI used so the page can be matched without broadcasting the permanent SUPI. If the wrong ID is used, the UE ignores the page. If a permanent ID were used carelessly, you would leak identity on the broadcast channel. Temporary IDs protect privacy while still addressing the device. The TAI list is geography. A tracking area is a cluster of cells. The UE performs tracking area updates as it moves, so the AMF's list stays current. When the AMF pages, every GNB serving those TAIs may be asked to transmit. Page too wide and you burn capacity across many cells. Page too narrow and you miss a UE that just crossed a boundary. The registered TAI list is the network's best current guess of where the UE can hear. Paging DRX is the clock. Imagine the UE checks its mailbox only every few hundred milliseconds or longer. On a schedule both sides agreed. The GNB must place the RRC page in a paging frame and paging occasion aligned with that DRX. Miss the occasion and the UE is deaf until the next cycle, adding delay or forcing retransmissions. Identity says who, TAI says where, DRX says when. Get all 3 right and the page is both private and efficient. Now the message leaves the core and hits the air. When a GNB, more generally an NG RAN node, receives the N2 paging message, it must page the UE in cells that belong to the tracking areas indicated in the TAI list for paging information element. Not every cell under that GNB, only cells inside the listed TAIs. The GNB builds an RRC paging request and sends it on the paging channel at the right DRX occasion. Multiple UEs can be addressed in one paging message on the air, each with its own identity record. Our UE listens, decodes, and looks for a match against its NAS paging identity. Why this split between N2 and RRC? Because the AMF understands mobility and registration geography, while the GNB understands cells, beams, and radio frames. N2 carries the policy and the scope. RRC carries the actual wake-up bits the idle UE can receive without an RRC connection. If the UE does not answer, maybe it moved, maybe the radio was blocked, the network may retry according to operator paging strategies. Those strategies are exactly where policy differentiation and priority come into play later. For a successful page, though, one clean RRC paging request is enough to pull the UE out of silence. The UE has seen its identity on the paging channel. What does it do next? It does not send a tiny "I'm here" ping and stop. The specification is clear. The UE is in CM idle on 3GPP access. Upon reception of a paging request for a PDU session associated with 3GPP access, the UE shall initiate the UE-triggered service request with PDU procedure. That service request reestablishes the NAS signaling connection toward the AMF. It also reactivates the user plane paths for the relevant PDU sessions, so the packet that was waiting in the UPF can finally be delivered. From the network's point of view, the UE transitions from CM idle toward CM connected. From the user's point of view, the call setup or app notification simply appears. Here is a concrete picture. You have a messaging app, a photo is waiting downlink. UPF buffers it, SMF tells AMF, AMF pages, GNB broadcasts RRC paging. Your phone wakes, runs service request, PDU session user plane comes back, and the photo downloads. The entire chain exists so that idle devices pay almost nothing in battery until there is real work to do. One subtle point, the page is tied to a PDU session on 3GPP access. The UE's response is therefore not generic. It is the service request that restores that session context. Paging is the alarm clock. Service request is getting out of bed and opening the door. Let us walk the sequence diagram end to end, the way it appears in the source. Left to right, we have three actors, UE, GNB, and AMF. The UE starts labeled RM registered and CM idle, our precondition box. Arrow 1, right to left from AMF toward GNB. N2 paging. On that arrow, ride the NAS ID for paging, the list of TAIs to be paged, paging DRX, paging priority, UE radio capability for paging, assistance data for paging, and paging origin. The AMF may send this to multiple RAN nodes that cover the registered tracking areas. Arrow 2, from GNB to UE. RRC paging request, the radio wake-up. The UE is monitoring paging occasions. It decodes and matches its identity. Then the UE box lights up, UE initiated service request. That climbs back toward the core, restoring signaling and user plane. Notice what is not on the diagram. There is no direct AMF to UE arrow for paging. Idle UEs have no NAS connection. The RAN is the only path that can touch them on the air. Also notice the trigger note beside the diagram. This can be started by the AMF itself or by another NF such as SMF or SMSF. But the N2 page always comes from the AMF. If you remember only one picture from this lecture, remember this 3-actor ladder. Everything else is detail inside those arrows. Not every page deserves the same strategy. That is the idea behind paging policy differentiation. It is an optional feature. When supported, the AMF, based on operator configuration, can apply different paging strategies for different traffic or service types provided within the same PDU session. Same tunnel, different urgency, different treatment. The source is specific about the knobs. Paging strategies may be configured in the AMF for different combinations of paging priority, DNN, the data network name, ARP, and 5QI. So the operator can say, pages related to IMS voice get aggressive retries across more cells. Background app sync gets a gentler, cheaper pattern. A particular enterprise DNN gets its own profile. Why inside the same PDU session? Because modern sessions multiplex many flows. A single PDU session to the internet can carry a Wi-Fi calling signal and a bulk photo backup at once. Without differentiation, the AMF would page as if every packet were equal. With it, the AMF looks at how the downlink was classified and picks a strategy that matches the service. For students, when you design or troubleshoot paging load, ask not only was the UE paged, but which policy profile fired. Differentiation is how operators trade success rate against radio signaling cost on a per-service basis.